Homework 2.6, Combinations of Functions, Video 2. Homework due on Friday, May 22nd, 2020 at 11:59 p.m. This is the second video about domains of functions, and so the same homework problems 1 through 8 still apply. In the previous video, we discussed the domain of polynomial functions, easy, all real numbers, and the domain of rational functions, all real numbers except those that make denominators equal to 0. The third and final domain issue we're going to, let me try that again. The third and final domain issue that we're going to look at in this video are radical functions. Now we're only focusing on square root, but generally this applies to any even roots, like square root, fourth root, sixth root, etc. For odd roots, like cube roots, there are no domain issues created by the radical, unless there are other things like denominators that create domain issues. Later we'll learn another domain issue when we get to logarithms, but that's down the road. All right, so let's talk about how to find the domain of a radical function. We've got 3 examples up here. Recall that the domain of a function is the set of all real numbers that make the function defined and real. By defined, we mean avoid denominators equal to 0, and by real, we want no square roots of negatives, more generally even roots, but we're only going to focus on square roots. So all of these obviously have square roots, so how do we go about finding their domain? Well, let's think about it and then we'll set up a strategy. Let's take a look at this first one. F of x equals the square root of 3x plus 9. I'm okay as long as the 3x plus 9 stays non-negative. It can be positive, it can be 0, but it can't be negative, hence the phrase non-negative. So what numbers will keep this greater than or equal to 0? Can I put in 0? Try it. Can I put in negative 1? Well, 3 times negative 1 is negative 1. What? 3 times negative 1 is negative 3. Negative 3 plus 9 is 6, and although the square root of 6 is irrational, it is real because it's a positive number under the radical sign. So what numbers will keep this greater than or equal to 0? Well, wait a second. I literally just described what I'm trying to make happen. In order for this to stay real, in order for this to not square root a negative, we need to make sure that the radicand, which in this case is 3x plus 9, is greater than or equal to 0. As long as this expression is greater than or equal to 0, we're okay. So why don't we just solve this? Subtract 9 from both sides, get 3x is greater than or equal to negative 9, divide both sides by 3, do not reverse the sign, that's not one of the moves that does it, and we get x is greater than or equal to negative 3. If we drew it on our number line, we would find negative 3. The numbers greater than that are to the right, and because it says or equal to, we would include it with a bracket, and so the interval would be bracket negative 3, infinity. Well, that wasn't too bad, and from this one example, I think we can generalize a strategy. To find the domain of a radical function, you solve radicand greater than or equal to 0. That's all you do. That prevents the square root of a negative number. Now, how difficult it is to solve radicand is greater than or equal to 0 is contingent on the radicand. For example, in this next one, g of x equals the square root of 9 minus x squared. The radicand is quadratic. That doesn't change the approach. We still need 9 minus x squared to be greater than or equal to 0. But you may recall from a previous video, I believe it was from homework 1.7, that to solve a polynomial inequality, the strategy there is to first solve the corresponding equation. 9 minus x squared is equal to 0. Let's not dilly-dally, the solutions are 3 and negative 3. But when you're solving a polynomial inequality, and frankly, any inequality, the solutions to the equation tell you how to partition the number line. So we would partition a negative 3 and 3, And then we would pick a test value from each partition, each interval. For example, we need to test something less than -3. We could test x equals -4. We need to test something between -3 and 3. Let's test x equals 0. And we need to choose a value greater than 3. Let's test x equals 4. Now remember, when you test them in the original inequality to see if it makes it true or false. For the sake of time, and to not drag this video out too long, we'll just verbalize whether or not these make the inequality true or false. If we substitute -4 here, it will square and become a 16. 9 minus 16 is -7, which is not greater than or equal to 0. That makes it false. We do not want the left interval. If we substitute 0 into the inequality, 9 minus 0 squared is 9. That is greater than or equal to 0. That makes the inequality true. We like that interval. And if we test x equals 4, 9 minus 4 squared is still -7, which is not greater than or equal to 0. Makes the inequality false. We don't want that. And so the solution to the inequality, and hence our domain, is the middle interval. But don't forget, as part of this inequality solving process, you have to decide on your interval, which is -3 to 3, the one in the middle, whether or not to keep the endpoints, but that's dependent on whether or not the inequality allows equality. Since this says greater than or equal to, we do want the numbers that make it equal, so we would use a bracket. In retrospect, this domain makes sense. If we pick anything bigger than 3, whether it's positive or negative, then when we square it, it will be bigger than 9. And so the answer to the subtraction problem would be negative and cause a problem. For this last one, you might be thinking it's the same as the first one, because isn't the radicand 3x plus 9 the same as over there? You're correct, but this radical function is the numerator of a rational function. I like to say that this domain has multiple issues. It's got a square root whose radicand we don't want to get negative, but it also has a denominator that we don't want equal to 0. When you have a function with multiple domain issues, you want the largest domain that satisfies both conditions. For example, we already know, based on what we did back here, that we need x is greater than or equal to -3. So I'm not going to resolve that, just look over there. But what do we know based on this denominator? Since we don't want it to equal 0, what can we not substitute for 5? We can't let it. I just gave it away. What can we not substitute for x? 5. So we have two conditions that we need to satisfy. We need everything greater than or equal to 3, but not 5. So how would that look like in interval notation? I don't know. Let's see what it looks like as a number line. Remember, when you put two numbers on a number line, make sure the lesser number is to the left. Most people do, but you'd be surprised. This first condition says everything greater than or equal to -3. So bracket because it says or equal to, and shade to the right. But slow your roll when you get to the 5. If I just shade in right over it, it's going to include the 5. And I need to explicitly exclude the 5. So I'm going to go ahead and write an open circle so it's clear that that 5 is missing. Although I did say in a previous video we don't write open circles, we write parentheses, but for visual purposes I think that's better right now. We took our half number line, if you will, and we partitioned it into two intervals, this one and that one. The interval on the left begins at -3 and includes it, but it stops at 5 and doesn't include it, parentheses. Since we have a second interval, it's time for a union symbol. The second interval begins at 5 but does not include it, so parentheses, and goes towards infinity. So the domain for this one is a little jankier, if you will. Have fun with that, auto captions on YouTube. But it does reflect both of the necessary criteria for this function's domain. Don't let it get less than -3, we won't. Don't let it equal 5, we won't.